Shall we start on time or not? So then I guess it's time to start. All right. Good morning, everybody. So first, you can find the material, including a few zip files with my Python notebooks, on this URL, and I've tweeted it also. Maybe I should have made a bit.ly link, but I didn't. So I'll leave this up the screen for a little while, so that if people have difficulties retrieving the slides.
You send it on the Telegram group.
You send it on the Telegram group. Thank you. Thank you. So what I'd like to talk about today is how can you understand basically how a machine learning model is working. And the short answer is that there is no short answer, that there is no magic recipe, that this is not easy. And I've divided a bit the tutorial in two parts. One is understanding and measuring how well a given model predicts. And the second part is trying to understand why it predicts. Okay? And I guess we'll just get started. So my goal is really to give simple examples that make sense of a simple phenomena. Most of the tutorial is using nothing more than scikit-learn and a few very simple data sets. And at the end, I'll be using the Lime package, but that's only for the last part. Okay? And I should probably blow up the fonts like this. And so I'm gonna switch directly to the first part and blow up the fonts. And if you want to download the notebooks, you just scroll down at the bottom of this part and you'll download all the notebooks for the first part, okay? If you're interested in downloading the notebooks. And so I'll switch directly to 1.1. So the layout of this part is, first I'd like to discuss which metrics are useful to judge the success of a given model, both in regression and classification settings. And then I'd like to talk about some gotchas with cross-validations, basically how to do it right. And then I'd like to talk about how to judge whether a model is overfitting or underfitting, okay? That's going to be the first part. So in this part, I'm only focusing on the prediction and not on the features or the mechanisms that predict. All right? So if you have any questions, please interrupt me. So moving to 1.1, metrics. And starting with regression metrics. And I'll just switch to the notebook, and you're welcome to follow either on the notebook if you want to run, but I'm afraid this is more going to be a shift-enter kind of tutorial in the sense that I haven't really prepared exercises because my goal is not really to do coding. The coding in here is all quite simple, but more to think about the data. And maybe where it's useful to have things in a notebook is that we can change the visualization to understand things better. Okay? So you're welcome either to follow along the web page or along the notebook. They're the same thing. So let me switch to the notebook. And let me start the first notebook. Okay? And let me hide things to retrieve some real estate. Oh, that's okay. Okay. Can I decrease the font a bit? Is this large enough at the back, Guillaume? With the screens, it's large enough. Okay, thank you. So, so as you probably know, you can do cross-validation in scikit-learn with a sklearn.model-selection.cross-val-score. And here we're going to be looking at data set, which is the Boston housing data set. So it's a housing data set. And it's shipped with scikit-learn, so we can load it with load Boston. And we're going to shuffle it in a given way. And then we're just this quick plot to understand what's in the data. What we're trying to do here is that we're trying to predict the price as a function of different features of houses. Okay, so the price of a house is a function of different features. So you can see that the price is in thousands of dollars. This is an old data set, so things seem cheap. And this is a function of the crime rate. So as a small note, it's quite important to look at your data. There's on this first plot, so here I'm plotting the price as a function of all the different features. And on this first plot, we can see a lot of things. One of the things that we can see is that the price tends to go down as the crime rate of the neighborhood goes up. I guess that's expected. But we can see another thing on this plot. Can you? There's a salient feature, at least to me.
It's capped.
It's capped, yes. So this thing here is capped. So that's probably related to the way the data was acquired. It's probably 50K or more. Okay? That's useful to know this. Okay, so then we can look at all the features, and of course we're going to have the capping on every feature, but so we'd have to understand those features. I don't remember what ZN stands for. Variable names are important. This is whether you're next to the Chase River or not. This is in Boston. The Chase River is a river in Boston. It's a nice area. This is the number of rooms, so you can see that the price goes up with the number of rooms. Makes sense. The age of the house. Older houses tend to be cheaper, but some of them are super expensive. Right, so many features that I don't fully understand. Okay? So then we're going to try to do what we do, which is we're going to predict. And so we're just going to use a standard vanilla predictor, which is the random forest regressor with default parameters. And then we're just going to measure its prediction accuracy using cross-val score. And we get 3 numbers. What are those 3 numbers? So the first thing is that in scikit-learn, we try to have the default that bigger is better. So we might not know what those 3 numbers are, but bigger is better. Okay? Then these numbers, so we're in a regression setting, and by default, scikit-learn uses the R2 score as a metric for regression setting. So R2 score is nice because it has a natural scaling. So R2 score is the fraction of explained variance of the data. So it's the fraction of the data that you're, of the variance of Y that you're explaining with your prediction. So 1 means that you're explaining which fraction, how much Y? 100%, okay? So that's really nice about R2 score is that when you get 1, you know it's an upper bound, you know you can't do any better. 0 is a round chance. You're explaining 0 fraction of the variance. And there's something that's surprising to people is that chance is actually slightly below 0. And the reason is that this explained variance is compared to taking the mean over the trained data. So if you give me a price of houses, the baseline that the R2 score uses is the mean of the training data, the mean price. And chance is actually worse than the mean price. Okay, so I'll come back to this. That surprises people. Another reason why it surprises people is that R2 score is most often thought in terms of in-sample statistics if you've got training in traditional statistics, in which case 0 is chance. It's out of sample that chance is below 0. Okay, but as a rough approximation, we can think of 0 as chance. And then you can easily get negative predictions. You're doing worse than mean. It's really easy to do worse than mean in machine learning. It's overfit, basically. Okay? So now, let's see which houses are easier to predict. And feature 3 is whether or not we're along the Charles River. So we can look. So we can basically select the samples that are along the Charles River and the corresponding targets, and we can try to predict from this. So cross-val score on this, and we get, so these are not along the Charles River, and these are along the Charles River. So which one is easiest to predict? Along, so no, I mean the ones where the score is highest is the ones that we're not along the Charles River. But of course, if I'm asking you this question, there's probably something settled there. And we can't really compare R2 scores across different data sets, because R2 score is the fraction of the variance of the target, but I have different targets. So if the variance of the target is different across those two data sets, I can't compare these things. Okay? That's an important point. So with some luck, the variance of the target is similar, so I can compare. But R2 score is a measure that is relative to the data set. So if I'm taking different samples, I can't compare.
Isn't there a distance from the Charles River and it's one of the features?
Yes.
Okay.
So, but I've selected the, I've subsampled my data set. I've taken only the houses close to the Charles River and only the houses far from the Charles River. Suppose that only the houses, I don't know if it's the case, we'll see, but suppose that the neighborhoods close to the Charles River were neighborhoods where everybody was rich, and so the variance of the houses were small. And on the other hand, you know, if you go away from the Charles River, you've got all kinds of neighborhoods, rich neighborhoods and poor neighborhoods. In which case, away from the Charles River, you'd have a lot of variance. And comparing those explained variance may not make sense. You know, if maybe you want to compare things based on dollars, not on explained variance. In which case, it might be interesting to use something like some form of mean square error, okay? Which has a different scaling. And this one is not dependent on the variance of the data or the target. So the way we change the measure reported by cross-val score in scikit-learn is that we use the scoring parameter that can take a string that describes what we want to use, and we can give it the mean squared error. But because in scikit-learn we want things to be bigger is better, scikit-learn doesn't provide the mean square error. It provides the negated mean square error. Okay? So we give it the negative mean square error, and we can compare along the Charles River and away from the Charles River. Okay? And so we're always in the setting where bigger is better. So our prediction here, which is away from the Charles River, is better than our prediction along the Charles River. Okay? And does this coincide with here? Yes, it does. So the adversarial setting that I was mentioning does not happen. But it's useful. I mean, we've had these situations where the variance of the target would change across data sets, and the conclusions didn't carry over. So it's useful. So one measure that I like a lot is mean absolute error. And so in scikit-learn, we have negated mean absolute error. And the reason I like it a lot is that it's really a scaling that is in the same dimensions than the target. So here I'm going to get a value that's a mean absolute error in dollars. Well, in $. So on average, I'm making an absolute error of $2,000 in the prediction here. So personally, this tends to be one of my go-to, these days this tends to be one of my go-to scoring measures because I can really report the error in a unit that makes sense to the end user, and it really has a simple meaning. Yours?
Can you do using the root mean squared error? You did the mean squared error using the root mean squared error?
The RMSE. We could be using the RMSE. I tend to prefer the mean absolute error because there's really natural linear scaling. Sorry? Right, it's an L1, L2 norm, but I mean, this one is really closer to things that you can report to users. So technically, in a given data set, what I do is that I will actually look at both these days, and I will look at the explained variance because at some point I know I can't do better than one, and so in a given data set, it's easy to understand. And if my unit is an arbitrary unit, it's easy to understand. But I will also look at the mean absolute error because it carries over across data sets, and because I can report it in a way that has a meaning. And I actually think, now reviewing papers, I actually think that people should really report both of these. Okay, any questions on this?
So is that denormalized then, or is normalization not something that's done at all?
The mean absolute error is exactly what it says. You take the predicted y minus the true y for each sample. You take the absolute value of this and the average.
So the data is not normalized then?
No.
Okay.
So it's really in the unit of y. And I think that's useful. So typically, how many dollars on average will I get it wrong? But I mean, at some point, you're going to have to go back to the application and think, what matters for the application? And maybe it's not the mean absolute error. Maybe it's something different. All right, any other questions on this? Okay, so let's move to classification settings. And for classification settings, we'll be using the digits data set. And so the digits data set is a data set that's shipped with scikit-learn. It's handwritten digits, but it's not the famous MNIST data set. It's a simpler one. And we're first going to start to try to separate sevens from something else. So as a target, I'll just use a vector of 0s and 1, which is whether a given digit is a 7 or not, okay? And I'll just be using a random forest classifier. And so we can just start with cross-val score. And so it returns a measure. What measure is this? What number is this? Well, first bigger is better, as always. And then do you know what this is? So it's the average prediction success. So if I have 1, it means I'm correct 100% of the time. If I have 0, it means I'm correct 0% of the time, which means I'm doing below chance. But that's something that happens a lot in machine learning. It's overfit. OK, so I'm doing quite well here, right? I'm correct more than 96% of the time. Now, in scikit-learn, we have what we call a dummy classifier. And a dummy classifier, the definition of the dummy classifier in scikit-learn is that it doesn't look at the data x. It might look at the target y, but not at the data. So it's not learning any link between x and y. And so I can use the dummy classifier, and I can tell it to predict the most frequent output, the most frequent y. In which case, here, we're getting around 90% accuracy. Why is that? So we're getting, I mean, if I report it to you, I'm getting 90% accuracy. Am I done? Can I go home? You'd probably tell me yes.
Is it because only 10% of the input is 7?
That's correct. So we have 90% of zeros and 10% of ones. So out of this data set, we have only 10% of the data set that is sevens. Okay? And that's the limitation of the accuracy score. So this score, we call it the accuracy score or the 0-1 loss if we want to be pedantic in machine learning. But one of the limitations is that I can interpret it only if I know the distribution of zeros and one, the distribution of classes. Okay? So that's an important caveat. And so there's one way around that's available in the latest scikit-learn, which is the balanced accuracy. Actually, I think I checked out, so scikit-learn 020 is not released, and actually I think I checked out, yeah, okay. I checked out 018 just before giving the tutorial to make sure that I was giving the tutorial on the same version than you. So if we were under 020, we'd get the balanced score, the balanced accuracy. And the balanced accuracy compensates for this so that I believe that 0.5 is always chance. Am I right, Guillaume? Yeah, okay, so 0.5 is always chance. I find it harder to interpret, but maybe that's just because I'm not used to it. Okay? So, in an unbalanced data set, or in a given application setting, it might not be the same thing to do a false detection or a miss. So suppose we're no longer predicting sevens and digits, but suppose we're predicting cancer. And so it might be a different thing to get it wrong and miss somebody who has a cancer, so in which case I'll call this a miss, or to have a false detection and predict that somebody has a cancer, whereas it's not the case. And it's important to go back to the application to know which is most important, because if I'm doing a prediction, if I'm predicting that somebody has a cancer and this person is going to go into brain surgery and we're going to remove part of the brain, then I don't want false detections. That's a very bad setting. However, if this is just a screening test, and then this person is, if I detect that the person has cancer, this person is going to go in a better, more expensive test that will be more reliable, then maybe I'd rather have false detections than misses. Okay? So it's different on the depending on the application setting. So in which case, it's useful to use concepts from information retrieval, which are precision and recall. So precision is the ratio of detections that are correct. Okay? So we can look at precision with our problem, and we find that 100% of the precisions are correct on 2 of the 3 folds. Of the detections are correct on 2 of the 3 folds. Okay? So this is telling us that our classifier is precise. It's well detecting sevens, but it may be missing. So I can reliably think that its detections are sevens, but it can be missing some sevens in my training set, in my test set. And so we can, by the way, the most frequent classifier will never predict a 7 because it's predicting the most frequent, and most frequent is not 7, in which case precision isn't very well defined, but scikit-learn puts it to 0, which is a good. So precision is a ratio, so that's why it's not well defined. So scikit-learn is warning you, but it's putting it to 0. So the opposite of precision is recall. It's the fraction of the class 1 that is actually detected. Okay? And so here it's the fraction of 7s that is actually detected. So which fraction of 7 are we detecting? And what we're seeing is that our classifier hasn't a great recall. It's only detecting a rather small fraction of the 7s. Right? We're missing many 7s. But of course, the most frequent classifier never predicts any 7. Okay? So, two different ways of measuring the error, precision and recall. It's important to keep in mind that measuring one without the other doesn't make any sense. I can be terribly precise by always telling you no. I will never get it wrong. I can have a great recall by always saying yes. So there's a trade-off between precision and recall. Okay? And so the ideal situation is that we should compare classifier on a precision at a given recall. So if I want to find 50% of the 7s in the data set, how precise am I with the given classifier? That would be a good metric. This didn't render well in the notebook. I should have checked. So let me go back to the web page. I added the figure to be didactic here. There we go. So many classifiers, I'll switch back to the notebook just after. Many classifiers provide a non-thresholded decision. The reason is that internally classifiers tend to use not a binary decision, but tend to have a graduated decision where larger value means closer to 1 and smaller value means closer to 0. Okay? And this in scikit-learn, this could be exposed via predict proba, in which case we have hopefully a calibrated probability of class 1. If I have 1, the classifier is pretty sure it's class 1. If I have 0, it's pretty sure it's not class 1. It can be anywhere between. Or it could just be a decision function. The decision function is uncalibrated. It's typically threshold at 0. Anything that's below 0 is class 0. Anything that's above 0 is class 1. But it's uncalibrated. So if you have a linear classifier, the decision function will basically be the projection of the data on the learned set of weight vectors. Okay? And so you can see that if you vary the thresholding of this decision function, or the probability, you're going to vary your trade-off between precision and recall. And I can vary from always saying no to always saying yes and exploring the different trade-offs. And so in such a setting, we can compute what's known as a receiver operating characteristic curve. So I've shown you one here. And the idea is we're varying this threshold. And as we're varying this threshold, each time we have a different compromise between precision and recall. Okay? Going from something that is extremely conservative, I'm thresholding really low, and is never telling me yes, in which case it's very precise with a very low recall, to the opposite situation. And the ROC curve looks at related measure, which is the false positive rate and the true positive rate. Okay? So we're really exploring the trade-off between false positive and true positives. And chances is the diagonal line. Okay? Because I always have the same fraction of false positive and true positives. And perfect prediction is a square that goes like this. Okay? And a good way of getting one number out of this is to look at the area under the curve of the ROC curve. So it's, in our jargon, we call it the AUC, area under the curve, and sometimes AUC ROC. Okay? which case chance is 50%. And perfect prediction, well, chance is 0.5 and perfect prediction is 1. Okay?
Maybe you said it, but how do you control the threshold in the random forest design?
So
Is it something that you can set yourself?
so the way you would do it is you take the, I believe random forest classifier has a predict proba. You take the predict proba and then you threshold it. And the reason that random forest has predict proba is because random forest is an ensemble classifier that's doing a bunch of different classifiers. And if they all agree, then it's probability 1. So if they all agree it's class 1, it's probability 1. If they all agree it's it's not class 1, then it's probability 0. And then you're just looking. Yeah. But you have the point underlying your question is, but in practice, if I want to set my false positive rate to 50%, how do I do this? Then it's known as a calibration problem. That's the word you need to look for. And you're going to be trying to, either on the train set or in a nested cross-validation, to set your threshold to achieve this target. Okay? And so if we want to compare classifiers over all trade-offs, we're going to compare the area under the curve of the RC curve. And in scikit-learn, the way you do this, and now I'm going to switch back to the notebooks. Sorry. In scikit-learn, the way you do this is simply you give, you can't see here, you give a scoring equals RC UC. And this will work only if your classifier exposes a decision function or predict proba, because if it's only giving you already decisions that are already made, you can't explore the trade-offs, okay? And so this is a good measure because it's really invariant to class imbalance. Even if I have rare classes, I will always have 0.5. So if you're with class imbalance that you don't master well, the ROC AUC is a good measure. It's one that you can really interpret as the higher it is, the better it is, and chance is always 0.5. Okay? So I personally like this measure to compare classifiers. That's my go-to measure to compare classifiers. Another related one is the average precision. So the difference between the true positive rate and the recall, or the false positive rate and the precision, is that they're normalized differently. So they're related, but they're normalized differently. And in some cases, it might be interesting to look at the average precision. So the average precision is related to the area under the curve of the rock curve, but it's with a different normalization. And you can show that one is a strictly increasing function of the other. And the average precision might make more sense for application setting. So it's varying the threshold, varying the recall. What's the average precision I get? Okay, and you can do this using scoring equals average precision. Drawback is that naive decisions are no longer at 0.5. But in information retrieval setting, average precision is often a good measure. Now, I've simplified the problem right now. So can I, in terms of screen real estate, well, I don't gain much by moving this. I can keep it here. OK. I've simplified the problem a lot because I've looked at only a single class problem. OK, I'm only predicting, so far I'm only predicting sevens versus something else. Many settings are multi-class problems, but in which case the precision and recall are less naturally defined. They're defined per class. So the accuracy is very well naturally defined in a multi-class setting. The 0, 1 loss. So we can still compute. So the difference between what I was doing previously and this is that here I'm looking at the full target. The full target is made of 10 classes. It's not 7s and not 7s. It's all the different digits. Okay. In which case accuracy is well defined, and we still get 1 is perfect prediction. Chance depends once again on the distribution of the labels. The most frequent label is no longer a very interesting baseline. And an interesting baseline is to basically do a random choice. Okay? So random choice in Y. So we can use the dummy classifier to do a random choice, in which case we see that the chance is around 10%, which makes sense because our data set is a balanced data set of 10 digits. So it makes sense that it's approximately 10%. So precision and recall are now specific to the class to detect, because the precision and the recall have the notion of a target class. Okay? So we can compute precision and recall per class, but we can no longer compute precision and recall for the multi-class problem. Okay? If we're computing precision and recall per class, we're actually no longer really in multi-class settings. And the reason is that when we're varying the threshold, okay, so in multi-class setting, I can't predict that something is both a 7 and an 8. Okay, that's not a multi-class prediction. It's not a valid multi-class prediction. But precision and recall do not take this into account. However, there's another setting that's known as the multi-label prediction setting, which is you have a bunch of different labels, and each time you're trying to predict whether or not a sample has this label. And you can think this as the Gmail inbox classification problem. When something comes in your Gmail inbox, Gmail tries to put labels to it. It might come from your friends, it might be work, it might be spam. In which case, several labels are possible per mail. Okay, so that's a multi-label setting. And we can always transform a multi-class setting in a multi-label setting. And for this, we can use the label binarizer, which is an object that is applied to the target, not to the data. Okay? And so what this will do is it will blow up my target, which was a 1D vector of digits going from 0 to 9, into a matrix that is each time a 0, 1 classification problem. Okay? Does that make sense? So,
why does it have more than 10 lines?
It's the number of samples. I've limited it to 15 samples.
So each row is one sample.
Each row is one sample, and each column is one target. So or one label. So now we're in a multi-target prediction and a multi-target prediction for classification setting. It's a multi-label prediction. Okay? Yes?
So it's like constructing 10 different classifiers, one against all the others?
Yeah. It's a bit like this, but at the end of the day, you won't pick one.
So you just measure the precision and recall for each.
And then yes,
one
right.
of these classifiers.
And then we can measure the precision and recall for each one of these classifiers. But in such a setting, I can no longer. It's just like if you were asking me, is this a 7? Yes. Is this a 1? Yes. Ah no, you can't tell me it's both a 1 or a 7. Difference between multi-label and multi-class.
Actually, for each row, it could be more than one.
Right, exactly. If this multi-label matrix did not come from a multi-class problem that we transformed into a multi-label one, then we could have several ones in it. Okay? And then the good thing is that now we can compute AUC for each label separately. So now with this new target, so that I call labels, not classes, I can compute the area under the curve. And then I get the average area under the curve over all targets. It's important to realize that it's not the same thing as, it cannot easily be related to the area under the curve of a problem that's a multi-class problem. The reason is that the amount of false positive and true positive will not correspond to the same threshold on the decision function of the different classifiers, okay? There's no universal, easy way of mapping one problem to the other. So now I can compute the average precision and all these things, okay? So to summarize, the first thing you need to keep in mind is that, in classification setting, is that the distribution of the Y target that you're trying to predict, so of the different classes, matter if you want to judge what's a good prediction. So both the distribution of the true Y, the true classes, and in this case, you're basically thinking of things like class imbalances. If all your classes are well balanced, then you don't need to think it over. But if your classes are not well balanced, then you need to think it over. And the other thing that you need to keep in mind is the distribution of your errors. Basically, a miss or a false detection might not have the same cost. If you're in single class setting, the area under the curve is a good way of looking at those trade-offs. If in multi-class setting, then I personally don't have a good way, and I'd be happy to discuss with people. Question?
Sorry, for the last thing you were saying about if you had, say, if it caught the first 8 things really, really well, and then the last 2 it got really badly, would you still have like a 0.8 score for these sorts of things, would you, or would it kind of go off?
That really depends on the class balance. Well, the first thing is it really depends on the class balance. Maybe the last 2 are extremely rare in your setting. And the other thing is I don't think you can guarantee that you can go from one to the other. I'm pretty sure you can create adversarial examples where it doesn't work. Now, in practice, how often do these happen? I don't know.
I mean, if you had a few columns that were really good, sorry, if you had most of your columns really good, on 1 or 2 that weren't very good, would it would just average them out and give you something that looked good, would it?
Are you asking me about the scikit-learn code or about the... So the scikit-learn code, if you go in the detail, there are different ways you can do multi-label AUC. And I'm not really good at this because I never do it, but one of them is taking into account the class imbalance. One of them is weighing them all the same way. Well, the label imbalance, not the class imbalance. Now, some labels may be more frequent than others. I don't know. My Gmail mailbox may have lots of spam. But that's we're always going back to the fact that this is application setting. This is application dependent. So I personally, the way I personally work, and I don't know if it's going to work for everybody, is I tend to look at the AUC of each class, and then I tend to think about what it means for my application. Does that answer your question? Reasonably. Any other questions? Okay. I'm going slowly, so we can switch to the next notebook, and I can kill this guy. Shut down. And we can switch to cross-validation. And I can toggle the header. There we go. Okay, let's talk a bit more about cross-validation. So we talked about the metric. Now let's talk a bit more about the cross-validation. And the first thing I'd like to talk about is the uncertainty of the cross-validation measure. So I'm just going to create some synthetic data. It's very simple synthetic data. It's two blobs. It's two Gaussian blobs, class 1 and class 0 and class 1. That are centered in 0, 0, and 1, 1. Okay? And I'm going to use a linear discriminant analysis on this data set, which happens to be the exact the base classifier for this data. So basically the perfect classifier given data, but it's also the simplest one, and it doesn't really matter in this part of the discussion. So I can do cross-validation on this, and the first thing we can see is that there's some variance across the different folds. So what does this variance mean? Well, it's just sampling noise, right? So what if I try different random shuffles of the data? So each time here, I'm going to shuffle the data and to redo this cross-validation. And so you can see that this varies quite a lot. If we took the best prediction, we'd have we have 76% prediction, I believe. 81, there's an 81 somewhere? Wow, 81. 81. Worst one would be like what? 59? Do we get worse than 59? All right, so between 81 and 59, there's quite a difference. And if I need to publish and I have a strong incentive to report the best one, I can report 81. So it's important to keep in mind that this is actually very easily understandable. And the reason is, this is very simple probability. The reason is, if you think your classifier is a coin flip, and ideally your classifier is not doing chance level. Ideally it's doing better at predicting than chance. So you can think of it as a biased coin flip, right? It's a coin flip that has a certain probability of getting it right. What you're trying to do is to estimate this probability of getting it right. And in the simplest case, everything is IID, your classifier, or the data is homogeneous. Each time you're measuring a coin flip. Okay, so measuring coin flips is a well-known distribution. It's the binomial distribution, okay? And it's the binomial distribution of probability, the probability of the coin, the biased coin, and of numbers of degrees of freedom, the amount of data that the amount of times that you've tried your classifier, which is the largest possible amount is the amount of data points you have. Okay. So we can plot this. This is just probability. So here I'm plotting it. And so this is, I've taken 0.75, and this is, what's important is that this is the distribution of the average classification accuracy observed over my 100 data points. Okay? But the average, not the single, because the single is always 0 and 1. Okay? So when I see this, what comes in my mind is it's wide. Okay? The point I'm trying to make is that just sampling noise, just basic probability, means that with only 100 data points, you'd have a certain width in your average cross-validation accuracy. And there's nothing you can do about it. It's just, you have only 100 data points. And by the way, this is the best case, because here I've said that the data was IID, there's no heterogeneity. I've not taken into account the fact that we're doing cross-validation, so we're actually coupling our different measures. They're not independent. So the immediate answer is, well, you got a small data set. You have 100 samples. So what I can do is I can use just probability. So to compute the interval in which 95% of the mass lies, which is, that's also the interval out of which I have 5% chances of finding data. So if you do empirical sciences like biology or psychology, typically you declare you're allowed to publish a result if you have only 5% chances of finding it randomly, by chance. Okay? The typically socially accepted threshold is if there's only 5% chances of it being by chance, you're allowed to publish a result. So this is why I'm taking this 5% interval, or 95% interval. And so I have a classifier that's distributed around 0.7, and I'm varying the sample size, and I'm giving you the width of this interval. With 100 data points, it's almost 20%. With 1,000 data points, it's 6%. With 10,000 data points, it's 2%. With 100,000 data points, it's 0.6%. With 1,000,000 data points, it's 0.2%. Are you getting the point? It's wide. So if your deep CNN GAN thing is doing 0.2% better than a linear model, you can't believe it. Even if you have 1,000,000 data points. Because this is just, it could just be sampling noise. And I myself didn't realize how wide these things were until I did those computations. And this is the best case scenario. Any questions on this?
So does this apply for all kinds of classifiers?
Yeah, this is completely unrelated to the classifier. I didn't put any model of the classifier.
When you want to estimate the noise in your score, is it better to do like you did, shuffling by hand the data, or just using the cross-val score? Can you increase the number of faults?
So it's a good question, and maybe I'll answer it afterwards. But basically, how do you judge this? Very good question. Yeah. So yes. You can do repeated cross-validation. However, and I'll come back to this. However, this will not solve this problem. What I've shown you here is something that is best case scenario. Your classifier is absolutely always estimating a reliable, same prediction accuracy. My data is IID, no heterogeneity. There's nothing you can do better than this. And in practice, it's always worse. Okay? I got two questions pretty much on the same topic. Any other question? I really want to stress that this is ideal, perfect setting, and we're never in those ideal, perfect settings. So then let's look at. Am I doing this? No, I'm not actually doing this. I should do this. Yeah.
Changing the K, the number of faults, does it change accurate distribution? For example, one out
So the question was, does changing the cross-validation strategy change anything? Am I talking about cross-validation strategies or not? Let me check my my notes. To avoid repeating me. I'm not. Okay, so I could, but I'm not here. So now I need to go back to where I was. Yeah, that's it. So, okay, so I got basically three questions that were on the same topic, which I'm unfortunately not covering in those notes. So the first thing is, no, there's no way you're going to get around this. No way, because what I've done here, what I'm showing you here is that I'm assuming that I'm given a data set. I'm given a classifier, and this classifier works in the sense that it predicts with a certain accuracy, but I've not modeled in any way here the fact that this classifier is dependent on the data. So I'm given 1,000 data points, and I'm given a classifier, and with 1,000 points and a classifier, I can only judge the there's no way, I don't have enough data point to measure this accuracy at better than 0.2. In practice, I'm doing something that's slightly more complicated, slightly more subtle. I'm doing cross-validation. So this classifier is not given to me from somewhere else. It's trained on data and tested on data. So in practice, it's something slightly more subtle. And then the problem is that, so then the question is, I can do leave one out. So people in biomedical imaging and neuroimaging seem to think that leave one out is cool. Well, it's not. And the reason is, when I get leave one out and I have n points, then I have n measures. And I have the feeling that I have more measures on the data than if I do tenfold, for instance. But the important thing is that those measures are not independent because each of those measures have looked at almost the same data in the trained data set. Okay? And so finding out the covariance between those measures, or the statistical dependency between those measures, is actually really difficult. And there's a paper by Grandvalet and Bengio, and Yoshio Bengio, in like the early 2000s that proved that you can't, in general, characterize this. You can always find adversarial settings that will break this. But maybe so the theory tells you there isn't too much you can say, but in ideal settings, you can show that there is a trade-off between the amount of data you put in train and the amount of data that you put in test, and that this trade-off lies typically around 10%. So typically, it's good to leave out 10% of the data. And then what you might want to do, so then you might want to do tenfold, but then you're thinking, okay, tenfold, it's kind of stupid because tenfold, I've taken one specific partition of the data and doing tenfold on this. Okay? So what you can do is that you can do repeated tenfold by like shuffling the data, or what we like to do is what we call shuffle split, which is you randomly subsample the data. You take 10% of the data, leave out 10% in, and you do this many, many times. But when you do this, I realize I should have done it here, but I haven't. When you do this, it's important to realize that you're not acquiring new data points on your cross-validation measure. You can't do a t-test between this and chance. The reason is that those data points are not independent. So if I do random shuffle split, I can do basically this random shuffle split as much as I want, right? I can just increase this number. It's just computationally demanding, and so this means that I could make any difference significant if I was doing significance testing on this thing, because I could get n to go to infinity. That's not the case. I could get the number of cross-validation to go to infinity. But I only have n data points. So I will never, have more degrees of freedom than my n data points. So the right way to think about this is that if I do a shuffle split, let me do it for you, I think. I think it would be useful. If I do a shuffle split here, so let me go back here and insert, okay, I'm going to kill this URL, and then I insert here, and I'm going to do many shuffle splits. So from Sklern, import model selection, and then shuffle. So CV equals model selection dot shuffle split, and then I'll do n splits equals 200. I can afford this, and I will retrieve the scores in here. So CV equals CV, and I'll print them. So I run this, bang, okay. Oh, interesting. The scores are discrete. Why are they discrete? Because counting statistics. But what I can do is I can plot the histogram of the scores. And then basically what you're seeing, it's kind of hard to see. I would, to get a better experience, I'd have to increase I mean, I can do this. I can increase the samples I have. Right now, my sampling noise is so bad that it's just hard to see anything. So I can increase the samples I have here. And samples equals, and I'm going to put 500 samples. And then I can go back. Now I have 500 samples, so things should, I should have less of a discrete setting, right? So, and now I can plot the histogram. Well, it's still noisy. I should maybe increase the number of splits. Where I'm getting at is this histogram is going to look a bit like my binomial I'm trying to estimate. Okay? And so the way you need to think about those scores is that they're not independent data points on your prediction accuracy that you're trying to estimate. They are more like a posterior on the prediction accuracy. And the setting we're in is closer to a setting of bootstrap than a setting of independent measurements. Okay? And if you want to read a bit further on this, you should probably look at the Bootstrap 632, which is a classic paper by, I believe, Efron, which shows the link between cross-validation and Bootstrap and suggests a good way of using Bootstrap-like method to estimate a posterior on the prediction accuracy of a given classifier. No, you cannot. You can get a posterior. What you can do is you can get a posterior, which is useful. It's very useful. So basically, you can calibrate what I was giving you here with simple statistics. You can calibrate it on your data. So it's the question that Emma was asking. But it's going to be worse than this, some bad news. But you can calibrate it on data in a sense that you get a posterior. And now this is going to be very subtle, but posterior, by the way, does not allow you to do classical, does not easily allow you to do classical hypothesis testing because it's a posterior, because it's not probability of the null.
Does it make sense then to report always mean accuracy and standard deviation instead of?
That's a very good question, and I'm very happy that you're asking it because it means that I'm not explaining things right. Because standard deviation does not mean anything on non-independent data. I can make my standard deviation as small as I want by just increasing the number of splits. Because standard deviation is basically going to be is divided by the number of splits, right? So I can make this thing as small as I want by cranking up my number of splits. So standard deviation does not mean anything on cross-validation. You need to report quantiles, okay? Does that make sense, the difference?
So this histogram is going to shrink if you're going to...
No, it's not.
Okay, so what I mean is the standard deviation of this histogram.
So you mean the quantile. What you mean is the quantile. Okay. Standard deviation is something that's related to the number of measurements you have. Yeah, so I think what's the right way to do this is to report the quantile of, so do cross-validation with many splits and report the quantile. I think that's the right way of judging your error. Nobody does this. I mean, we've noticed this issue 2 years ago, and we've started doing this. And I guess other people are doing this, but it's very seldom the case. And outside of academia, it's also important. The question is, are you fooling yourself? This is a posterior. This is the chances that you'll observe this given your data. Okay? Any questions? So the take-home message here was cross-validation is a noisy measure. There's nothing you can do about this. Okay, I'm gonna start speeding up, and the way I'm gonna speed up is I'm basically gonna skip this part, on measuring baselines, because this part is just, the take-home message here is the dummy classifier is something cool, you should be using it. Because it's too easy to fool yourself in terms of what's the chance. But there's nothing clever here. So I won't take the questions on it unless you've got burning ones. Okie dokie. I've been going really slow, so I can do two things. I can jump to interpreting models, or I can talk about, so interpreting model and model weights, or I can talk about overfit and underfit. Overfit and underfit are more classic things. They tend to be mentioned a lot. You should also know about them. So let's do a show of hands. Who thinks he knows reasonably well trade-offs between overfit and underfit? Well, not reasonably well. Who has already heard trade-offs about underfit and overfit? Who has not? Who doesn't care because they're checking mail or Facebook? All right, so based on this polling, I think I'm going to skip to the second part. So now we're skipping to part 2, okay? And on the website, this means going back to the index and then switching to understanding why your classifier predicts. And you can download the notebooks at the bottom of this. Okay? So why? And I'll start with linear models. Okay. So I'll start with linear models. And why linear models? Because linear models are easier to interpret. Well, people think they are. I think they are too. So, and I'll start with data on wage, which hopefully this should allow you to download it and to load it. So this is basically a classic data set on wage. It was quite a while ago that has different features describing individuals, and one of those features is the wage, the amount of money the amount of dollars they're making per hour, and we are going to try to predict this, the amount of money that they're making per hour. So can people run this? By the way, is this running on?
What's the name?
Sorry.
What's the name of the notebook?
It's going to be, it's in the section 2, so 2, and it's going to be interpreting linear models. So the first one. So for this, you need to download another zip file. Okay. You need to go to section 2 and download another zip file. That's why. Okay. And so hopefully the data download worked for you. And what I'll do, by the way, is I'll take the log 10 of the wage, because wage are typically vary exponentially. Okay, that's a classic problem with money. Money varies exponentially. And I'll call this wage. And then let's just look at the pair plot of this data. Okay, so pair plot. If you don't know what pair plot is, then so I'm using seaborn.pairplot, and data is appended data frame, and then I'm giving it the variables I'm interested in, so the column names, and I'm basically interested in wage, age, education, and experience. Okay, and we could add other things like gender of people. It'd be interesting, but. And so what it's giving me is it's giving me the scatter plot of one variable as a function of another. So, okay, I'm going to hide the toolbar, and then later I'm going to regret it. But life. Okay. There we can fit approximately things on the screen. Okay, so for those in the back, the order is wage, age, education, experience. Okay, wage. First one is wage, what we're trying to predict, then age, then education and experience. And each time we have the scatter plot between the two. So experience age, experience wage, experience age, and this is how it works, okay? And so scatter plot is an estimate of the joint distribution, okay? So what can we see here? Well, things like wage increases slightly with education in some settings. Well, maybe it's easier to look at here. Wage education, you can see that the maximum, this is kind of fun actually. This here is wage as a function of education. So what you can see here is that maximum wage increases with education, but minimum wage doesn't. So if you're educated but clueless, then you won't be well paid. Good. But probably if you're clever and not educated, you won't be well paid. That's sad. Okay? There's another striking feature here. I mean, if I look at this, I see something extremely striking.
The age and experience are really well correlated.
Right, age and experience are extremely well correlated. It kind of makes sense. You know, I can't have 10 years of experience if I'm 2, or 20 years of experience if I'm 12. Yeah.
How is experience defined? Is it number of years of experience?
I think it's probably number of years of experience. But let's keep this in mind. I mean, they're heavily correlated, right? And let's keep this in mind. Okay? So I don't have code for this, but the link between, where's that? The link between experience, no, it's the link between education and wage is what I will call a marginal link, okay? And the reason is that this link is only looking at wage as a function of education and not as a function of other things. I'm not looking at the joint distribution between everything. I'm just looking at the joint distribution between wage and education, all right? So that's something that's going to be very important in this part of the talk, is that I'm doing multivariate statistics. I have many features. The underlying statistical problem is a multivariate, so a joint problem in a probability space that is of a large dimension, but I can only look at projections, so marginals or cuts, conditionals. Does that make sense? I'll probably come back to this. Okay, so what I've observed here is a marginal link between wage and education. It is not telling me a link between wage, education, and age, for instance. And there might or might not be one. So if we're using univariate feature selection, so it's clern.featureselection.select k-best, we're testing only for marginal links, testing only for the link between one feature and the target, okay? But if we're using a linear model, we're actually testing for conditional links because we're trying to fit a link between all these things together. So we're testing for something that is not easy to see in this plot, right? So the difference between conditional and marginal is going to be the crux of everything I'll be talking about in the second part of the tutorial. So if you don't understand things, just please do stop me. So by conditional, maybe I'll explain things a bit better. Marginal, I have two variables. I have wage and age, or wage and education, and I'm looking only at the joint distribution between those two. This is what I'm going to call a marginal link. Conditional link, I would be looking at the joint distribution between wage and experience, conditioning on age, which means for a given age, if I'm 22 and I have 7 years of experience, how does this, well, if I'm 22 and I have X years of experience, how does these X years of experience relate to how much I'm making? Is this the same at 25, at 30, at 50, at 60? So this is the link between experience and wage conditionally on age. Okay? That difference is a very important one. And importantly, a linear model is learning conditional relationships. So now I'm just going to try to predict using a linear model. I'm going to use the simplest linear model I can use, which is the ridge regression. And then I'll visualize the coefficients of the ridge regression. So I was looking to see if there was a blackboard, but there's none. So the linear model is basically telling me that wage is the linear function of the different features, okay? And the coefficients are the weight that it's putting on each of those features. And so this is what I'm looking at. So I guess MAR, I believe, is marital status. Sector is some indicator of the sector of activity. Race is, I guess, 0 is probably white guys, and non-zero is probably something else. Age is easy. Union is 0, not in a union. 1 in a union. Experience, we know. Sex is probably, well, given that it's negatively correlated, I would say it's probably 0 is women and 1 is men, but we'd have to check. My bias that women tend to be less well paid. South is, I guess, where you're employed, and education is the years of education. So the first thing we need to keep in mind is that we cannot really easily compare the size of those bars because the data is not standardized in a given way. Okay, so if I have more variance in I don't know, education than age, I can't really compare these things. Well, it's more likely to be the converse, right? More variance in age than education. All right? So that's the first thing. And I can standardize things in here by, well, I won't do it in terms of time, but I could standardize these things. The second thing that's really important to understand is that all these things are conditional relationships. So age and education, we saw that, well, we should see that age has a strong impact. Where's age? Age and wage. So age and wage is here. Okay, we can barely see, a better plot would show this better, that there is a link between age and wage. It's basically wage goes up with age. Okay? But what we're seeing is that conditionally on experience, then it doesn't go up with age. And we're seeing it from here. We're seeing that age doesn't have a large impact, but experience has a larger impact. And the variance of these things are going to be approximately the same. Okay? So we cannot say that age is unrelated to wage. This would be wrong. But we can say that conditionally on experience, age is related to wage. Okay? And so first take-home message is that interpreting linear models is done conditionally. And then the second thing that's important is that those linear models are estimates of the conditional relationships. They're not the expectation of the conditional relationships. We need to estimate these things from the data. And this estimation is non-trivial, and it's not something that we like to talk about because it's ugly and dirty, and we like to hide our problems. But the only reason that we can estimate these things reasonably well is because, so we're in high dimensional settings, we have many variables and a limited amount of observations. And the only reason that machine learning works is because it has regularization, okay? And regularization, ridge, which is the go-to linear model, is a specific kind of regularization. Another kind of regularization is these sparse models, like Lasso, which try to pick a subset of the features to see which one are importantly. So we can use a Lasso to do this. And so as I told you, the Lasso will try to put certain things to 0. And this is the model that we're getting with the Lasso, and it's put basically 2 things to 0, which is experience and race. It's interesting that it puts race to 0. So can we conclude that, well, after all, experience was not important. It's age that's important. So no, and it's quite subtle. Why? The experience variable will have more noise than the age variable. It's harder to measure experience than age. The regularization is slightly arbitrary. It will pick some things, in particular when 2 things are heavily correlated. So those 2 variables are extremely heavily correlated, and I'm trying to estimate conditional relationships, conditioning on those 2 variables. So conditioning on correlated variables is something that's extremely hard mathematically, statistically. Okay, it's ill-posed. So basically, I can't really conclude from the data whether it's age or experience that matters. And the reason is that they're heavily correlated, and I would need a lot of data and very good data to conclude. Okay? So I can have biases. I think it's experience, but testing for correlated predictors is going to be extremely hard because this conditioning is hard.
Is experience used calculated as number of years spent in the same field, or is it calculated as, I have 10 years of experience, like I started to work like 10 years ago?
I don't know. This is not a data set I acquired. Okay? So other take-home message is the model is partly arbitrary. It's using tricks such as regularization to be able to estimate from the data. These regularization come in with specific biases. It's a bias-variance trade-off, classic in statistics. And you need to understand these biases to interpret well the model. So that might, get you down the rabbit hole because you might have to learn a lot about a model. In general, when 2 features are extremely correlated, it's hard to interpret one conditionally on the other. Okay? And there's just about nothing you can do to this, right? Or you need to be an expert to avoid this problem.
Is it always a good idea to normalize data? Because you told me that the variance basically in every single section, feature, is actually not a good proxy to compare 2 different features, right? Because the variance in one can be different from the variance in another one. So is always a good idea to normalize data? Because there are some fields where, normalizing is a good idea, but you're actually filtering out some things that are happening real in the market, I'm an econometrician, so I work mainly with financial markets and stuff like that. When you normalize data, you are literally filtering out the fat tails observation that you have at extreme. So I don't know. I'm just asking.
No, the question is what you're trying to do. So where we're getting at is it's a different problem to interpret a model and to predict best. And so maybe the right way to do it, so if you normalize, it's easy to compare coefficients of a linear model. But maybe the right way to do it wouldn't be to normalize the data, but to compute the variance of each predictor and then to normalize the coefficients by the variance. Internally, scikit-learn does something a bit like this. Okay?
Okay, thank you.
Yeah, 5 minutes. So one thing that we can do is that we can use, I'm going to speed up. I'm definitely not going to cover everything, but I'm going to speed up. And one thing that we can do is that we can use stability as a proxy for significance. And so this is what I'm doing here. Oh, and then of course speeding up doesn't work. Oh yeah, because I switched back to 0019. I should have done this. So basically, okay, I'm going to stick to very simple take-home messages. Stability, looking at the stability of your coefficients is a good thing. And maybe I can switch to the notes, because these have run under 018. So here, 020. So here I'm looking at stability of coefficients, and I'm using a function that's only in 020. And so I'm running I'm running many times. It's related to the bootstrap I was doing earlier. I'm running many times the analysis, and then I'm aggregating coefficients many times. So this is basically telling me the variations of coefficients under data perturbation. And then I can plot no longer one single bar, but basically a box plot of the coefficient. And this is done doing a lasso, doing many times. And so then I can see how things vary, and it gives me a bit more trust in my coefficients. And it does not solve the problem that experience is noisier than age, and hence experience gets set to 0 more than age. But in general, it's a good thing to do. Perturb your data, look at how stable the model weights are. Okay? Now I've switched to rush mode in the interest of time. So now I'm going to just very quickly, I talked a lot basically, so now I'm going to very quickly cover a few other things. One of them is random forest. So it's the same data set, and random forests give you one tool. Random forests are a more complicated model than linear models. And it's harder for me to have very simple message like it's conditional, it's marginal. But they do give you something that's useful, which is the feature importance. So you can compute feature importances, and you'll find them in feature importances in scikit-learn. And so the feature importance are basically an estimate of the mutual information between the variable and the target that is conditional on the neighbors and the trees that was being built. So it's kind of something that's in between marginal feature importance and conditional feature importance on the others. Okay? And actually, you can switch to be a fully marginal feature importance if you put the tree depth to 1. So you're not conditioning. But basically, as you move along your tree, you're conditioning. Okay?
Is this sort of like component analysis?
Well, component analysis is a linear model.
Yeah.
So, but it's like a weakly conditional mutual information. And you can see that it's weakly conditional because experience is not fully removed by age or vice versa. There's importance of both, okay? And one caveat is that when you look at categorical features, the number of categories actually tends, so for a very large number of categories, it tends to increase the feature importance arbitrarily. Because the way feature importance are computed, this is completely an artifact of the way they're estimated. So one thing you can do is calibrate this on permuted data, so data where there's no information, but there's no really good way of doing this. It's still a useful measure, okay, but it's not a magic bullet. Okay, so I keep moving. Partial dependencies plot. So what are partial dependency plots? So scikit-learn has tools to compute partial dependency. It's not that hard for gradient boosted regressors. What a partial dependency plot, let me just explain this plot. So we're back to Boston housing, and we're looking at the impact of crime rate on the price of a house. Okay? And what a partial dependency plot is, it's the dependency of how the cost of the function varies as a function of the crime rate, marginal on all the others. Okay? So it's the link between price and crime marginal on the others as estimated by the model. And then you can do 2D partial dependency plot is I'm varying crime rate and number of room and marginal on the others. So summing on all the others, okay? So it's basically conditional, it's wage conditional on crime and room and marginal on the others, okay? There isn't much more to it than that. And so I can switch to the last thing I want to talk. So I'll almost be in time. And I'd like to talk about LIME. And LIME stands for Local Interpretation of Model something, I don't know. And LIME is two things. It's a package, which is called LIME, and an ID. And here I'm demoing the package, but I think the ID is what matters most. The idea of LIME is that you're going to do local explanations. Is that if I give you a room, LIME will take the predictor and will compute the gradient of the prediction. Okay? So basically LIME will, so if I give you a house to predict, LIME will vary the features of the house and see how varying the features of the house impacts the prediction. Okay? By doing this, it's able to do some form of local, it's a gradient. It's basically, it's computing the gradient of the predictor's decision. And so it's able to, as it's a gradient, the gradient is in the same units than the original data, well, in derivative of the units. So then it's able to give a local explanation. It's for this room, if I varied well, crime rate didn't, apparently for this specific house, crime rate didn't pop up, okay? And so it can do this for any model, okay? So it's basically a local explanation. And this is another explanation. So the nice thing about LIME is that it gives you the idea that you can do local explanations. The link between partial dependencies and LIME is that partial dependency is local in one variable and global in the other. So it's conditional, so it's local in the variable it's conditional on, and global on in the variable it's marginal on. And so, you know, to go back across models, linear models are kind of a specific thing because they have the same decision logic everywhere. Whatever is the sample that you're giving, they're making the same decision rule. But more complex models are making different decision rules for different functions. So in terms of interpreting is something I hear all the time in my day job. In terms of interpreting, you really need to define what you want to interpret. And in some setting, partial dependency plots are good because they give you an overall view. But if you're an insurance broker and somebody walks in your shop and is asking you, why didn't I get the insurance, or why didn't I get this loan in a bank, then you can use a local interpretation on this person and tell him, you know, if you had this amount more money, then you would have gotten it. And it's a local thing. It's not a global thing. All right? So maybe two take-home messages. You need to think about conditional versus marginal relationships. Conditional relationships are extremely hard to estimate. Ideally, this is what we would like to have, but we can't always have them. And so there's model variance and model bias in them. And then you need to think about global versus local interpretations. And global, and they're going to match only in linear models. Okay? And that's all I have. And I'm available for questions. By the way, there's more in the notes if you want to look at them. Not every part is well written.